Fific. I will just call him Professor Mario. Professor Mario got his bachelor's and master's degree in Belgrade, Serbia, and Montenegro. I don't know your country is separate. In June 2006, 14 years ago, or 18 years ago. And then he moved to the United States and got his degree with none other than Jim Thompson. And then he worked as a postdoc with Dr. Nosowski, and also worked at the Max Planck Institute in Berlin. And in 2011, he became a faculty member of the Grand Valley State University in Michigan. It's not associate professor. As you probably already know, Professor Mario again has done a great deal of work applying the systems factorial technology, starting from the face perception, which is really one of the favorite topics to faculty doctoral thesis, and then move on to other fields, including most recently decision making. I think we're going to hear a lot from him this morning. So without further ado, please join me to welcome Professor Mario. And the topic of his talk will be analytical transformation of facial holism, unveiling reverse alchemy through computational model. Professor Mario.
I would like to echo my previous fellows about the amazing hospitality that we've been able to receive here in Taiwan, and thank you for an opportunity to share ideas about and share enthusiasm about the science. So this is like a rare and great opportunity for all attendees. So thank you so much. Thank you, Cheng Ta, for organizing this presentation, and all the students and the faculty who collaborated and helped for this event to occur. So here's my second talk. Today, unlike the first talk, I introduce a novel approach in the facial recognition that has these foundations in the previous ideas. These ideas are usually we identify as the systems factorial technology. We see how some of these ideas from this suite of methods and approaches as a system factorial technology will be carried over to another level to bring this topic about facial perception into cognitive focus. So my collaborators on this project are Cheng Ta Yang, here Professor Yang, and David Little, who was also the member and attendee of this conference. Probably, if there was something that there's one thing that's talking about, he probably would be very happy, to join us. He was not able to do so. So anyway, this is like a long-term project. My question is, tell me what you see quickly. All right, so the students, that I give the first talk, I use the same slide. So very interesting, we can see some of you clearly identify identity of the person, right? And remember, my question was, what do you see? I didn't ask you particular detail. So technically, we could consider faces as some form of objects, but because they have some special meaning for us, we directly jump at the highest level of representation for such objects. So I can ask you another question, and this is where the part, from the previous presentation is, what was the shape of the nose of that top Taiwanese tennis badminton player? Can someone tell me and bring in their memory or consciousness the shape of the nose?
Might be triangle.
So let's see whether we can do that. We can go back, to the original picture, and then now instead of seeing the whole face identity, we can can focus on the nose. Can you do that? I mean, you can do that, right? You can see the shape of the nose. It pretty much seems like ignoring everything else. It looks like, we can also attend the facial features, right? Now we demonstrated two major types of modes in cognition and perception that deals with the facial perception. And although it's a very complicated process, the research in this topic divided between two approaches, between assuming that faces are stored in an analytic fashion as features, and then on the opposing side, we have this idea that the faces are used or stored maybe as a whole unit. This would be holistic perception. How this works, how you were able actually to use a brain to do these different types of tasks. Well, when I ask you, and when you're reaching for the identity, for the whole facial representation, you're probably somewhere around here, right? So this is the infratemporal cortex. So there's a fusiform area that is, researchers in neural studies found that this area is dedicated to processing whole faces. And then they, some painstaking research with the electrodes, even with the humans indicating, that faces seems like, whole things over there, right? But that will only explain one task, right? When I ask you to focus on feature, well, you have to ignore the faces. So you couldn't really go there. You have to go somewhere else. And where is that somewhere else? Now, the good thing is we know organization of the visual system from the research so far is that it starts to be something like hierarchically organized. That means the processing, pretty much serious processing, starts after LGN, to the V1, the part of the cortex, here at the back of our heads, in which what we only can see, there's a many of identifiers, that is a specialized neural cells that identify edges and lines of different orientation and size. Right, so this is how processing starts. And then slowly, if you move, to the higher level, to the cortex, V1, V4, and then we can eventually go to IT, we can see, whole objects. Each time something has been added, to the complexity of the stimuli, and it seems like at top, they become, whole objects. I mean, it could be face, it could be just maybe object perception, right? So it seems like, when I ask you about the facial feature, you are probably able to go from here, right, to seeing the entire face, to somewhere over here, maybe even over here, right, to pay attention. All right, so the question is then, how do we switch between two different modes of the facial perception? How do we go from holistic to analytic? And how do we go from analytic processing to holistic? So here's one dimension that kind of shows the continuity of the problem is analytic one is analytic hypothesis about analytic facial encoding assumes faces are broken down into facial features. Right? That's what we have stored in our brain. And then holistic assumes that we have whole faces, some kind of template or exemplar. So as Jim suggested last time, as a grandmother cell, right? Cell that seems like be dedicated to detecting one particular stimuli. So how do we switch between the two? Yeah. So that is actually the same question: is how do we travel, through these brain structures? Right? So how do you ended up, maybe focused in the infratemporal region, and how do you go maybe lower? Now we don't know that from the cognitive tasks, and then some of the tasks may be not really informative, but this would be the first step maybe to try to bring together these two approaches. So the first one is about the integration of the holistic and analytic within the same framework. Let's build a mathematical framework, computational framework that can bring them together. Why do we need, merging these two together? Well, there's been, I'm not sure whether you're familiar with the literature, but there's been like split in the society of researchers, and some researchers think, the faces to be only analyzed in a holistic fashion. They propose the strongly holistic hypothesis. But some other people, will challenge that and say, well, we have this analytic processing, then we use this build-up. There's a big kind of a rift or division between the researchers. And although some may take one side or the other side, I and probably some other researchers say, oh look, why don't we just bring them together? Let's see how they work together, because we just demonstrated that they can work together. Right? The second one is how to understand the spatial processing when they're combined with the high-level cognitive processes. They're not really part of facial perception, but has to do with the other important steps, such as maybe memory representation and decisional processes. So how that works in an entire framework. All right, so the two challenges. We think, my proposed solution to that problem is the assumption of the following kind of a fun-looking structure. So this is what is I define as a modular serial parallel network. And I believe such a network has been built into our cognitive systems. Maybe there's some kind of a very close representation of what it is in terms of the neural structure. But I can probably try to identify some of the structures in the cognitive model, maybe with some of the properties of the neural systems. But you know what, neural area is not I'm not expert into this area, so I may need help for someone else. No, this is my, mere suggestions, how the connection should be done. But anyway, this framework is actually called modular serial parallel network. It assumes that in the essence we have two modules to analyze perceptual stimuli. One that relies on serial processes, that means usually analyzed one by one, and the other suggests that we can do things in parallel. But it can does more than that, because it involves some kind of rule decision making that I explained a little bit, signal detection theory, mental architectures, a little bit more complicated than just pure serial and parallel, and then involves evidence accumulation from the cognitive brain structure. And it can actually help us to define the representational level of facial processing, decisional, logical implementation, modularity between the items. And so probably the similar approaches, to this kind of a network would be GRT to some extent, and this could be, one can make some parallels and similarities between the two, but there's some other approaches, such as the approach of Adele Dietrich. She has almost like a complete model of serial parallel processes, assuming all kinds of relationship, with these processes, that could be applied in a similar fashion. Now the thing is, this is kind of suited, to the visual object perception and the memory functions. So let me explain a little bit what is happening here. So we start usually with the object representation, where it's broken down into features, like we showed you in the V1 region in the visual cortex, in which object features, whatever they are, right, whenever we think of them, are stored as a continuous dimension. Stimuli as a kind of a point value, as a noisy representation here. For example, this green point here, this green distribution is a noisy representation of one maybe facial feature, maybe the badminton player's nose. Right here are the other noses of some other people, maybe, right? When you have the form of these noses and they stretch across the dimension. So here's another feature, yet another, so you can have, line of these features. So we assume, this is like a first level. And when faces has been presented to us, that these features could be activated. Certain regions, kind of being activated, just in the memory representation, right? So that they give us kind of a stronger signal. So here they're green. Now, after they've been presented here, we need to combine these features together. So one of the questions that we also learned about system factorial technology is one of the dominant questions that Joe Haupt highlighted is that one of the dominant problems is to understand how do we combine all this information from different sources. And here are different sources here, and this is the system of combining them together. Right? So before they start to be combined in a particular fashion, we have to decide whether that feature has been isolated, from the feature space. So we use, decision lines here, decision boundaries that tells us, whether the feature belongs, to the category that we find, associated with the task. Usually, when you think of a binary task, the task is: did you see that particular stimuli or not? Does it belong to the yes? It could be because category B, or it is no, that's not a feature of interest here, so we know. So you can also turn this into a categorization task. Does that feature belongs to the category B groups of objects that we're searching for or not, category A. So this decision line help us to separate, this decisional space to narrow down to find the particular feature that you will use for the decision making. This looks like, this stage looks like single detection theory. If you can detect, probably if you can observe, which is usually assuming some kind of noisy representation of an object, decision boundary that can move left and right. It's pretty much under our control, and these will be like a memory stored representations. Right? So once the decision line has been put, we need to accumulate evidence and to clean it out from the noise. So how do we know that this is actually the feature that we're searching for? Well, we need the accumulator here. Accumulator in this MSPN model are considered to be random walk. Very similar discrete version of maybe like Drake diffusion processes, maybe you're familiar with that one. So this kind of accumulator here that I simplified in that way picks up randomly information from the region of where the feature is, and that sometimes picks the noise, sometimes picks the correct information. All depends where this line is positioned. If this line is like a cutting through the feature of interest, well, maybe you will be actually sampling some kind of evidence that is not consistent with the decision making. But because these things are actually not under our control, we can really move them left and right, to try to extract the best features we can. The process of accumulation stops as soon as we reach a certain threshold criteria, and then this detector says, oh, I see that's the nose. I recognize that. See Mario's nose. Let's pass it up further. And the other feature detectors works, in the same fashion. So they could detect, these features and provide information. Is that everybody okay so far? So still information is some kind of an analytic form. So all this kind of independent sources of information. And they are actually handed over to this kind of a highway lane here, this highway lane for simplicity, but it's not actually a road to travel. It is just a bunch of wires here that, depending on how we position them, could either imitate sequential analysis of these features, sequential combination, if you put them on the same lane, one after another, so you can follow the sequence to feed them to the final decision maker, or we can do them in parallel. This is like a parallel network. If they're positioned on different kinds of separated lanes, they all go a life of their own, and they'll be analyzed in parallel, go to the final decision maker. The final decision maker stops as soon as the target has been detected. The target is in this case, correct category membership, so it's either left or right, depending on how you position this line, so that once the target is detected, the answer will be triggered, and you actually combine these features together, eventually reaching the level of phase identification. If you don't find the features of interest, then this is the other category, so you will actually exhaustively analyze all the features. We see now the second property of this network, which is termination versus exhaustive processing. The system can terminate to find the target and then proceed with the decision. If it doesn't find the target, it will just process them all. And there's a third property of the system, which is something that we really learned to likely to identify with the facial and holistic perception, which is feature binding and feature gluing. Feature gluing happened before we are combining them in the serial and parallel fashion here. So you see these are the lines that are connecting detectors from the sides. So technically these are channels of the communication between feature detectors. They could be closed. If they're closed, they vanish. So these roads are closed, nothing is going on. If they're open, and they could be open as a tap water, you can completely open it, you can mildly open it, then the information from each detector has been shared with the other detectors. What consequence does it have? If the channels are open just for the communication, if both detectors are analyzing the correct, or I would say correspondent feature that belong to the same object, their total effort to analyze individual feature will speed up. And this we call this facilitation. This is the case in which this detector analyzed category of feature B, or category B, and this analyzed category A, sorry, A and B here. So these guys will highly likely inhibit each other, right? But these two, A3 and A1, if they exchange information, they will facilitate each other. So it depends on this kind of a type of a communication, types of information they're exchanging. The system can either facilitate, and if they facilitate, this is equal to increasing the correlation between the feature detectors. Increasing the correlation means making them the same. And if these channels are fully open and there's a case of the facilitation between channels, this is what we usually see recognized in the theory as the feature binding, or creating higher level feature representation. Because if the channel allows them to be exchange information that is congruent across facial features, then we started to see combination features. The amount of that communication can change depending on the numbers here that specify the channel openings. All right, so 3 features we have described so far these networks. I'll show you how MSPN could be applied as a theoretical and exploratory tool. The first one will be providing theory for the underlying cognitive processes itself, and the second one is to provide the basis for analysis and hypothesis and model of validation of the other approaches. So the first one is acting as a theory itself, because it's like a full processing model. It can explain, choice preferences, probabilities, and then response times. But we see that the other role that could be played by this kind of a network is also exploratory. So you can use someone else's model and try to identify whether this kind of a system will point, to the same structure or similar structure as suggested by the other theory. So you can use this as for the model falsification and validation. This is the stuff that we usually think about SFT, is used for, this kind of exploratory meta theory tool, to falsify and validate, certain theories and approaches about cognitive organization of cognitive processes. But this is a little bit serious now, really assuming really that this is what is happening. We see the 2 roles kind of can be played relatively well. So I'll show you both cases. So how you can hierarchically represent features, again, as I described, these 3 features are key to understand hierarchical representation of the objects in the perceptual system. The first is, possessing basic features. Is actually the property of analytic analysis, right? So analytic encoding assumes that by default, we have these features installed, they're kind of could be separately accessed here. Decision bounds here are used, to separate the brain regions here. They play some role, but it's not quite evident, how they're playing the hierarchical role, except, they could be used, to explain some more complicated things, which I don't want to go there here in the details. Evidence accumulators can explain how do we get different biases and responses. You can bias responses to one or the other category, and then at the same time, because they accumulate evidence, they weed out the noise from the manual representations, and present them in a clear fashion into our conscious perception. Features gluing another property, which kind of binds them together, and then feature processing order combines them in a serial and parallel fashion, finishing it up with a certain kind of set of logical rules, that we use, to make final decisions. All right. So hierarchical organization could be aligned very nicely with the work of Professor Townsend and Michael Wagner. So this is one of the most important contributions to many of us, in the domain of holistic perception. Which is if you're going from left to right here, going from analytic to holistic processing, so how do we increase, this hierarchical level of the representation here? So Professor Townsend and Michael Wenger, in a set of papers, provided, several now almost axioms about them. The first one is that the serial process is by the default is less holistic than the parallel. So these guys here, should be analyzed in a serial system. These guys here are more likely with a parallel system, right? More holism, more parallelism. That's the first idea about the organizational process. The second one is about the scope of the search. Termination, early stopping, should be allowed for analytic processing. So termination is less holistic than exhaustive processing. Exhaustive processing is to process all features. That's by the definition. whole thing, right? If you can terminate, they're highly likely you are dealing with the features. Right? The second one is about the process dependency. So the dependent processes are likely to be holistic, remember the gluing aspect, and independent processes, are likely to be analytic. So you have three properties: processing order, scope of the search, and process dependencies. By setting them up, to be the second property, we are gaining more holism. Right? If you're losing any of these, we are getting more analytic processing. That makes this structure of the hierarchical representation of faces, and the network pretty much follows that properties. Okay, now here's how much time, how I'm staying with time. Good. So now first, we'll look at the theoretical validation. So this is MSPN considered as a theoretical conceptualization of the visual perceptual system. So we use a face categorization task. This task is actually done together in collaboration with Cheng Taiyang, and then some of the Taiwanese participants, as well as the people, some participants from the Western countries, helped, to collect this information. Categorization task, faces presented at a time, you have to decide whether this face is A or B. And faces are actually represented in this factorial fashion. Remember systems factorial technology, one of the key advantages of this method is that you use factorial manipulation of stimulus properties. And with this factorial manipulation of stimulus properties, you can use factorial tests. And proven by the theorems of the work of the Townsend and their colleagues, we know that this combination itself, this factorial manipulation, this orthogonal manipulation of stimulus configuration properties, creating 4x4 stimulus dimensions, should help, identification of serial and parallel properties and properties of processing order and process dependency here. So what we see here is mouth position and eye separation. So two face configural properties. They change different amounts. So we have 4x4 faces. From the distance, they all look very similar, but if you come closer, you see the faces here are becoming a little bit different. Here they're more spread out. Here they're more compact. So are individuals able to use them to make a classification of faces? So we assume, that in the facial space, features are represented in noisy representation associated with each of these facial property here. This is the comparison phase that you learn that compare your cases with. Your task is to classify this group, category A group and category B groups. To classify faces in category B group, you have to actually analyze both features. But for a category B group here, these guys over here, single feature could trigger a correct response. For example, if you see that mouth separation is really of that value here, you can figure out quickly, that you don't have to look at the other property, which is eyes. So you can just say, oh, that belongs to B, right? But we cannot do that for these guys here. That forces us to use different termination rules. And then this is another schematic representation of what is happening with spatial analysis. That these representations have been pulled into the modularity in one of the structures. So on a trial-to-trial basis, according to the MSPN, analysis could be serial or could be parallel. If they are serial, we see that the two accumulators, random walks, steps in or discrete steps in time, accumulate evidence coming from these noisy representations, and they have to reach a certain boundary. When they reach the boundary, we can recognize the face. So this is like a serial system. This one can stop here, but doesn't have to. They can proceed maybe to the second feature if necessary. So this is like schematics of the serial exhaustive or terminating system here. However, this, prior to each trial, you can actually switch to one of those modules, serial parallel. So let's say that if you are predetermined to go to the parallel stage, then the two random walks will accumulate this evidence in parallel. And in a certain case, as soon as they reach the decision, they will give their verdict about the features. In the case of the pooling information, remember where if you allow for the information to be shared across the features, you can see how that property has been shown here. Two random walks, but the black line is sum of the two random walks, which is kind of required, which is the description of the information exchange between channels of processing, right? So they're faster, right? So this line, the sum of these two lines here goes faster marching toward the decision boundary, speeding up the analysis. All right. So this is what is happening. Short walk here. Another look at the stimulus dimensions. We have this